Welcome everyone. So yeah, it's time to start, and Francesco is already here, and we are set, I think. So this is the answer set programming session. I guess, yeah, unfortunately, most of us are joining still virtually. Uh, but anyway, we are used to that, and let's come to the first paper/talk with the title Modeling the Outlier Detection Problem in ASPQ. And this is joint work by Pierpaolo Bellusci, Giuseppe Mazzotta, and Fracesco Ricca will give us a nice presentation.
Thanks, Martin. So after briefly introducing the problem, I will just talk about how to model problems beyond NP that are very hard with ASP. Then I will focus on our solution, on how to compute outliers in a population using a new formalism called ASP with quantifiers. And then I will draw the conclusion. So what is the outlier detection problem? The outlier detection problem is something that can be applied to many scenarios: fraud detection, network robustness checking, predictive maintenance. Is basically singling out anomalous individuals from a given population. So this problem that is very well known, especially in the machine learning and data mining community, was also presented and considered in knowledge representation. And in particular, Angiulli et al. In a TOCL paper in 2007 defined this, the meaning of outliers also in the setting of logic programming under the stable model semantics. And actually, this definition by Angiulli and colleagues defines a very complex problem that is hard for the second level of the polynomial hierarchy. So what was our goal in this paper? They had a solution modeled in ASP. We wanted to provide a more elegant one and also a more efficient implementation. So, and for doing this, we used this extension of ASP with quantifiers that I will describe in a while. Of course, we compare with the existing solution. So we are talking, of course, of answer set programming. I guess that everybody here knows this is a declarative programming paradigm that is based on logic programming, roots in data log, efficient systems, a lot of applications. And one of the key properties of ASP that is solved is that ASP has a powerful language. It can model basically all problems that are on the second level of the polynomial hierarchy. And you can write very uniform and compact encodings. I mean, you fix the logic program and you only change the facts to get to solve the same problem for different instances. So if one applies the so-called guess and check methodology or generate, define, and test methodology, which is basically the same thing, you can build a modular and compact solution for complex problems. And it is well known that ASP provides such a solution for problems in the NP class. This is an example we always use. Just two logic rules to encode the very well-known free colorability problem. However, what about modeling beyond NP with ASP? Well, this is possible, we know, we already mentioned it, because with unrestricted disjunction, stable model checking becomes a NP complete problem, and you can enforce basically this. Don't know why, I have to say. Maybe it's just too slow, Simona, the connection. So I will try to share.
Sorry.
So let me do a different thing.
You start sharing your screen again, because there was some visual artifacts. There were some visual artifacts when you were sharing and changing slides.
Okay, so I will do again. Can you see it?
Yes, Francesco. Now we are back to the right slide.
Let's hope that it works now. So as I was saying, that it is possible to model beyond NP, I already mentioned it. It is possible with unrestricted disjunction, and you have to use the minimality of answer sets, basically to encode more complex conditions. This is rarely elegant and compact. I see that my slides are not, let's say, well displayed again, because I changed something, so you see, it doesn't work. So I will try to do a different thing. No? Sorry for that. Stop. Okay, so I will, I'm using now the software.
Yes, now the transition works.
Okay, very good.
Works, yeah,
so I will try to reach the point. Okay. So this is modeling problems beyond NP is rarely elegant and compact unless one can find the positive encoding. This is the case of the well-known strategic companies example, but in general, if you want to go beyond NP, generate and test doesn't work, and you have to resort to the so-called saturation technique, in which you have to add a lot of symbols that don't really are part of the original problem, so to say. And Martin knows very well that unlike the ease of common ASP modeling, going with ASP beyond NP, it's something very, very involved and not easy to do. So this is why ASP with quantifiers has been introduced. Basically, the idea here is that you are quantifying over answer sets in a theory in which each program can be prefixed by a quantifier. Let's look at this through an example that is easier. A program in quantified answer set programming is like this. You say there exists a stable model of program P1 such that for all stable models of program P2, the constraint program C is satisfied. So in this example, we have a simple disjunctive program P1, another P2, and then C. So first program has two answer sets. Let's fix one. Then we use this, we add it to program P2, and we check whether for all answer sets of P2, and in this case, we have two answer sets, A1B1 and A1B2, constraint C is satisfied. Then when we add constraint C, we notice that this is not satisfied, so we come back and we try A2. So now let's check whether with A2, together with program P2, we get an answer set that is actually satisfied by the constraint. So it's easy to read. There exists a stable model of P1 such that for all stable models of P2, C is satisfied. So it is easy to see that going this way, you can model any problem in the polynomial hierarchy and also the outlier detection problem. So we want to identify anomalous individuals, outliers, in a given population. And as I said, this is a typical problem in the data mining community. But of course, when you just learn, maybe you can get out with poor generalization, while if you are able to model background knowledge, so the standard way the program is expected to work using an ASP program, then you can understand easily, just while reasoning, which are the outliers. So Angiulli et al. Provided the formal definition of outlier in ASP setting, provided complexity results and an implementation. What we did in our paper is a novel encoding using answer set programming with quantifiers, which is more compact and elegant, and also that results in a more efficient solution. This is the definition of outlier. Instead of going into the technicalities, let's look at it from the intuitive perspective. So we have a program, P rules, that models the system behavior. And we have a set of observations, P obs, a set of facts usually. So outliers are observations that are anomalous with respect to what the background knowledge would have implied. And just because we can find the witness, another set of observation, that is explainable only if all the facts in our outliers were not observed. So consider this example in which we have a network of computers that is displayed in this figure B, let's say, and basically a computer is down if his predecessor is up, okay? If not, his predecessor is up, okay? And then if you look at the agent knowledge that is modeled by using the program in the figure side A, you will notice this definition, okay? Now, together with this program, P rules, we have some observations, and we know that A and C are both down. Well, this is rather strange because you see, before A, S, the source, is up, and also this part of the network that is called the witness set that you have here on the right, all those guys are up, but C is down. And this is not compatible with what the background knowledge would suggest. On the one hand, if you look at A, we notice that the fact that A is not connected is not contradicting the program. Look, the program is stratified. It has only one model. On the other hand, if without the presence of C that is down, well, we would never know that this witness set is up. So actually, the witness set in figure B cannot be connected if C is not connected. So not only we know that C is down, the fact that C is down doesn't agree with the fact that all the remaining computers that are below C, after C in the network, are up. This is not expected with respect to background knowledge, so C is an outlier. So basically, this amounts to checking those two conditions that we have here, condition 1 and condition 2, in which we just pick the program, we keep out the witness, and we cannot imply the witness, basically. But if we remove both the witness and the outlier, then there is no way to derive the witness. Looking at this, if we pick this program and we just keep out from the observation the witness, we are not able to derive that all the computers in the witness set are connected. But if we remove also the outlier, then it is clear that they will never be derived from the background knowledge plus the knowledge on the network. This is not the case for A, and you can check it. So basically, we have to encode the two conditions, and to do this, we guess that the strategy in the encoding is to guess the outliers, guess a witness, and then we model the first condition. Notice that outlier the definition of outlier can work either with brave and cautious consequence, as we considered the brave inference. So basically here we are saying that to check the first condition that can be easily modeled by two rules, it is sufficient to check the existence of an answer set. If there exists an answer set of this program on the left that doesn't derive the witness, we are okay. Condition 2, instead, we have to check for all answer sets, because you see, this doesn't bravely entail, so there is no model, you have to check for all. And then we impose that both conditions are satisfied. To make our encoding more general, we also resort to a rewriting function that basically it's only a way of simulating with function symbols a renaming of the program, okay? So look, row of X of this rule, A of D, if B of D, not C of D, is we only take every single predicate or atom or literal in the rule, and we put it inside the function symbol, okay, to make copies, basically. And then this is our encoding, okay? So there exists what? A program. We take the original program P rules and we put it inside function symbols with predicate C1. The same for observations. Then we guess observation and witness, rule 5 and rule 6. And then we encode in rule 8 and 9 the first condition. Okay? Then for all defines the second condition. We just take another copy of the original program. We check condition number 2, and then with constraints in rule 17, 18, and 19, we just check that the two conditions are met in all quantified answer sets of the program. This that you see here is taken from the paper by Angiulli et al. This is, and it takes 2 slides, okay? 2 slides to do the same thing in plain ASP. And as you can see here, there is a lot of SAT, C1, and whatever. This is the base for these saturation techniques that you may know or not. But what I wanted to show you with these slides is that our solution is much more compact and easier to read than the one proposed by Angiulli et al. Then, taken this specification, we have a system, a solver, and this solver can be used as for plain ASP to run our specification. We compared our solution with the one by Angiulli et al. With networks of different sizes. Basically, the benchmark is based on the example that I was showing to you before. And as you can see, basically, our solution can scale up to graphs of larger size. And actually, the original one was working only for very small networks, while we can go up to 3 orders of magnitude networks that are 3 orders of magnitude larger than the previous solution. So in conclusion, outlier detection in ASP was basically a promising use case for showcasing answer set programming with quantifiers. The new solution is more compact and elegant than the previous one that was based on ASP. And the experiments confirm that not only is more compact and elegant, it's also more efficient. Future work, okay, working on the Brave semantics, but if you look, the Brave semantics encoding can be obtained just tweaking a little bit, just inverting the for all and exist part. It's very easy thing to be done. But also we want to explore more problems in the polynomial hierarchy where ASPQ can be an option to provide more compact and elegant solutions. And that's all, and I hope I could also recover a little bit of the time lost because of the, let's say, sharing problem. I'm done.
Thank you, Fracesco. You are still very good in time. And let's see, how does it work with the questions now? I don't see the audience, of course, but yes, either one can type it or ask for getting the control.
I don't know. I guess maybe they can write a message in the chat. This is for sure possible.
Yeah, I don't see one yet. It was a bit, that's very nice. I mean, that you got in the experiment much better results than a pure ASP solution, say, somehow with this second level complexity. And I think you showed the modeling language, but either it was a bit fast or I didn't get it about the implementation. Do you yourself compile to ASP again, or do you use some procedural solution that you do different queries and combine them?
So, Martin, we recently implemented the system that for this ASP answer set programming with quantifiers, okay? So this system is basically based on a rewriting on QBF. So in this paper, we just model the problem, take our implementation and run it as it would be Klingo or DLV, okay? But the implementation is basically based on a rewriting on QBF. But it's still not published, okay, but it will hopefully at some point, okay. So,
very interesting. Okay, we have a question here from the audience now, from Fracesco Calimeri. Apart from outlier detection, have you applied the formalism to different real-world problems?
well, Francesco, we are applying it to several other problems. We applied it to model new problems in the argumentation coming from the abstract argumentation frameworks. And also we modeled other very nasty problem in Sigma 2 that were very difficult to be modeled before. So this is a new formalism, and the implementation exists since 1 year, and it's not even published. So we started doing precisely what you are asking for. We are using it to solve more problems. So I think the answer is this. So I see also a question from Ezra.
Yeah. It's not shown yet, but I can read it if you like.
Yeah,
can the problem be solved via epistemic logic programming, where there are syntactic constructs in the program talking about if some atom is true in all answer sets, etc.?
Well, Ezra, this is a very interesting question. One could try to do this also using epistemic logic programming, because actually I think the final constraint is basically, I think it could be expressed in epistemic logic programming. Even if I think I don't have the written solution, but I can imagine one, so likely it is feasible. Also because this that you are asking for is just the final constraint, so I think it is feasible. So, and you don't even need strange cycles, okay?
Okay. Do we have further questions from the audience? We are still good in time.
So maybe I did a strong acceleration because I felt I lost a lot of time with this.
It wasn't too bad, and probably not your fault. One more question, maybe? How do you, I have one, what's always the bottleneck somehow with those disjunctive formalism is the recursion, right? If you, or say, in this testing part that somehow goes for the counterexamples, you cannot use negation. That's kind of the problem, which makes it very tedious. Do you have a nice way to deal with that?
So usually, if you have to express something with negation in the for all part, this saturation becomes a mess, right? Because if you can express it through a positive program, it comes for free, basically. No? That this for all condition. But this, at least to my experience, this is very rare that you can find examples in which you don't need negation in this tough condition, in the CoNP check. So in this way, using this ASP with quantifier, you don't have to care, because you just write your program precisely as you would have done without thinking about the need to saturate or to do something in the Redux. So it's just about modeling the definition as it is, and looking at the guessing part, let's say in the exist quantifier, and separately to the for all, to the condition that has to hold for all, and you write two ASP programs for the two conditions. Then they speak each other. So to my experience, this is it turns out to be more easy to write, whatever you have to write. No? And if you jump to the third and fourth level, I know problems there are less famous maybe, but this becomes even easier if you have to jump to tougher problems.
Okay. Thank you again, Fracesco, for this nice presentation. It worked really fine, so I clap.
Thanks, Martin. Thanks for everybody, and sorry for accelerating a lot, but I really felt I was I lost a lot of time with this sharing stuff. Okay,
Yeah.
bye bye.
Don't worry. Thank you.